So last week we ended with average rate of change versus instantaneous rate of change and what that was. And we were getting into one of the main concepts of calculus, which is the derivative. And so I'm looking for my writing utensil, which I should have had available before I started. Let me just find that real quick. Okay, so for some reason I can't find my Surface writing tab, and I wanted to show this video anyways. That kind of gives you an idea of what the derivative is. And we're just about to jump into what the derivative is. And when we were looking at that instantaneous rate of change on a function at a particular point, that's pretty much what we're talking about, the derivative or the slope at that particular point. And so here is a great video that kind of explains the derivative and the essence of the derivative and different ways to kind of look at it. So I'm not going to record this video, but you can find it. It's called The Paradoxes of Derivatives, and I'll link it to the homepage on campus. So if you didn't get to watch it during lecture, you can go back and watch it. Okay, so we just finished watching a video on 3 blue, 1 brown, the paradoxes of derivatives, and kind of went through and kind of explained what the derivative was. So again, we were looking at the average rate of change versus the instantaneous rate of change last week. We looked at the difference quotient, and this is the definition of the derivative, which uses the difference quotient. And so I pulled this from your book. Some good tools to know is how to read a math text. So I am just going to kind of go through this and then we'll talk about it. So we're going to start. So looking at the derivative. So if we have some function y, and a lot of times we denote y with function notation like f of x. So if f of x is a function and a is a number in the domain, then we shall use the symbol. So it has an F with a, what is that called? They call it a prime, parentheses A. And so we denote this with a special limit. Okay, so if we're looking at the derivative at a particular value A, which is defined in our domain, we're looking at the limit as h approaches 0 of f of a plus h minus f of a all over h. And we're saying provided that this limit exists. Okay, so this means for each number a, we can assign the number f prime of a found by calculating this limit. This assignment defines an important new function. Okay, so this is our derivative. The derivative of our function f at x is defined as f prime of x, the limit as h approaches 0. The numerator f of x plus h, and then minus f of x. And that numerator is all over h, provided the limit exists. And that notation, we read this as f prime of x. And we say that f prime of x is called the derivative of f with respect to x. So again, it's important to know what values of x are in your domain of f, and if f prime of x exists. Then we say that f is differentiable of x, and the process for produces f prime of x is called differentiation. Okay, so let's go back and talk about this. So let's just say again, let's pictorially, let's just show some f of x, some function f of x. And if we choose some value x equals a, so anywhere on the graph, I don't know where I want to go, how about right here? So when x equals a, this is your f of a value. This is your y value when x is a. And so what we're doing is we're choosing some other point on the graph. So let's say right here for now, which is a distance here of h. So if I go over a distance of h here, then this value right here, this would be considered a plus h. Okay, so my x value here is a plus h. And so this y value, oops, so it got a little bit too high. This is f of a plus h. And so if we look at the change of our y value, and sometimes we write this with a triangle to say change of y over the change in our x value. So another way we say this is rise over run, another way of looking at our slope. Okay, so let's look at our change in our y value. So our y value, right, this is f of a plus h minus the other y value, which is f of a, all over, so the x value that we started with would be a plus h minus this x value here, which is a. And so notice that this reduces down here a little bit. This is f of a plus h minus f of a all over, well, in the denominator, we have an a minus an a, so those cancel out all over h. So now if we take that concept of a limit, like we were looking at earlier in the course, and we let this h value go to 0, so it decreases and it shrinks down, so we're getting closer and closer to a. So this would look at the limit as h goes to 0 of f of a plus h minus f of a all over h. So if we went in here and we used our rules of limits and we plugged in 0 wherever we saw an h, we would end up getting this f of a minus f of a, which would cancel out, which is 0, all over the denominator, which is 0. So remember when we got indeterminate forms, that 0 over 0, that didn't tell us anything, and we had to go back in and we had to manipulate things. Things are going to start to fall out though when we tend to plug these back into our function when we know what f of x is, and we'll be able to manipulate this. But this is what the derivative is. This would be the derivative of x at this value at a. And so again, as this is getting, right now, we would say this is the average rate of change. But as h is getting 0 and 0 and 0, this is where we call it the instantaneous rate of change. And the instantaneous rate of change, we say, is that slope here of the tangent line. So when I kind of think about the slope of the tangent line, I kind of think about, okay, if I have a car and I'm driving on this function here, and I'm moving left to right, and it's nighttime and I have my headlights on, where would my headlights be pointing as I'm driving? And that's basically kind of the idea of where the slope is. And so, you know, if I came over here, let's see, over here, and I'm trying to figure out what the slope is, right? And I would be driving out here, my headlights would be, well, they'd be kind of pointing out this way. But if I was driving up here, my headlights would be pointing out this direction. Or if I was driving here, it's kind of horizontal, maybe a little bit decreasing. So that's how I kind of think of about my derivative at a point, is how, where direction would those headlights be pointing, and then extend it behind the car. And that's the name, which is the tangent line. Okay. So I had done just some value, a particular a value, but this here, this definition we can use, sorry as I try to blow it up, for any value at x. Okay, so let me just kind of now go back and start reading again. So I'm going to read the note. So the derivative is a function of x, since f prime of x varies as x varies. This differs from both the slope of the tangent line and the instantaneous rate of change, either of which is represented by f prime of a that corresponds to a number a. Otherwise, the formula for the derivative is identical to the formula of the slope of the tangent line given earlier in the section, and to the formula for the instantaneous rate of change given in the previous section. Okay, so the derivative has several interpretations, two of which we've already just discussed, and we have discussed in that last section. So the derivative f prime of x, this represents the instantaneous rate of change of y equals f of x with respect to x. So talking about business, this instantaneous rate of change could be interpreted as marginal cost, marginal revenue, or marginal profit, if the original function represented cost, revenue, or profit. Okay, so if we have a profit function and we take the derivative of that, then that's talking about the marginal cost, the rate of change of that cost function. Another interpretation of instantaneous rate of change for other types of problems, where we could talk about velocities. That video talked a lot about velocity, the rate of change of the car. So, or velocity, if the original function described displacement along a line. So from now on, we'll use this rate of change to mean instantaneous rate of change. Okay, so another way to interpret this derivative, the function f prime represents the slope of the graph of f of x at a point. So if the derivative is evaluated at a point x equals a, then it represents the slope of the curve or the slope of the tangent line at that point. And so that's what I was just showing you with that graph back up there. Okay, so we looked at evaluating last week this f of x plus h minus f of x all over h. We saw that this was a couple things to denote this. This was the slope of the secant line. We denoted this as the average rate of change between 2 points. It's also the average velocity, or we think of it as the average rate of change of cost, revenue, or profit. But once you throw in that limit in there as h approaches 0, so that's our only difference, we now call that our derivative of our function. It gives us the slope at the tangent line. It gives us the instantaneous rate of change at a value. It gives us the instantaneous velocity, and it gives us the marginal cost, marginal revenue, or marginal profit. Okay, so it really just depends on what your question is asking you to do, but pretty much you're doing the same thing. And just recognizing those are all representing the same thing, just depending on what type of problem you're looking at. Just as we had alternate previous sections by using b instead of h plus a, which I didn't like to do, but we could. We now have an alternate function by using b instead of x plus h. So instead, if you wanted to write it like this, you can. I tend not to use this alternate form, but it is in the book, and you might see it. Okay, so yay, we get to jump into some problems. Okay. Okay, so let's use the definition of the derivative and find f prime of x. So use the definition of the derivative, which I'm going to put right down here. We're going to use the limit as h approaches 0 of f of x plus h minus f of x all over h. To A, we're going to find f prime of x. And let's do, first example, let's do f of x is equal to negative 2x plus 5. So we want to find f prime of x. Okay, so we need to go back in here and we need to do this. You can do it in pieces if you want, but this is going to equal the limit as h is approaching 0 of, I need to go in wherever I see an x, and f of x, I need to go and plug in x plus h. So I'm looking at the limit as h approaches 0. Okay, so f of x, I have negative 2. I see an x, so I'm going to plug in x plus h. I'm just going to put parentheses there for that moment, plus 5. And then I have minus f of x. Well, f of x is this function right here. So if I subtract off that whole function, be careful because there's more than one term. We need parentheses around that. If I subtract off that whole function, minus 2x plus 5. And then it tells us to put this whole thing over h. So just go back in, and that parentheses, I needed that x plus h. So we're just going to clean it up by distributing. So because we haven't taken the limit yet, we're just going to bring it down until we plug in that 0 wherever we see an h. And let's distribute this negative 2 to each term inside the parentheses x plus h. And so if we do that, we get negative 2x minus 2h. Let's bring down that plus 5. And then let's distribute the negative outside. Distribute it to the negative 2x plus 5. So distributing the negative there, we get minus 2x. Actually, plus 2x. And then minus 5. And this is all over h. So just like that video said, things tend to clean up really nicely. It looks messy, but this negative 2x and this plus 2x, those cancel out. We have a 5 and a negative 5, those cancel out. And so really we have the limit as h approaches 0 of negative 2h left in the numerator all over h. At this point, if I plug in 0 for h, I get 0 over 0, telling me I need to simplify. Both of those cancel, the h cancels, and we get the limit as h approaches 0 of negative 2. Remember, the limit as h approaches a value of a constant was equal to that constant, equal to negative 2. So that's telling me that the slope of this line is equal to negative 2. So f prime of x is equal to negative 2. Well, let's talk about it. Doesn't that make sense? If we go back and we look at what our equation was, it's actually an equation of a line. F of x was y equals negative 2x plus 5. This is, again, equation of the line, y equals mx plus b. Notice that we can see what our slope is. In this form, our slope is -2. If we graph this line, I have a y-intercept at 5, and I have a slope of -2. So if I go down 2, and I can think of this as -2 over 1, if that helps. If I go down 2, I'd go over 1 to the right. If I went down another 2, I'd go over 1 to the right. And so any value on this line, any point that you choose on this line, your slope is always going to be -2. So that one wasn't as fun, but that was just the first question, was to find f prime of x. The next question was to find f prime of certain values. Well, if this is f prime of x, and it wanted you to find, let's say, f prime of 4. Well, if you go back into this function and you plug in 4 wherever you see an x, well, there's no x there. And so if you go back and plug in 4 wherever you see an x, it's still just 4. I'm sorry, it's still -2. Okay. So the slope at any point they gave us for a line is going to be what the slope of that line is. Let's say they changed it, and instead let's find g prime of x. And let's say g of x is given to us to be 6x squared minus 5x minus 1. So looking at this equation, I know I have a quadratic. So I know that, and I can see that my value of a, the number in front of my x squared, that coefficient tells you which direction your parabola faces. I don't know if you guys remember that. But if a is positive, your parabola faces upwards. So this is going to have a slope, different values depending on where I am on this parabola. It's going to be, my slope will be decreasing at some values. You'll notice that your slope actually is going to equal 0 at this minimum point, which we'll talk about later, which is your vertex, and then it will start increasing. So this won't have a constant slope everywhere like that line did. And so we want to find the derivative. So g prime of x is equal to, the limit as h approaches 0. So we're going to go in and we're going to go and plug in x plus h, whatever you see in x in your function g of x. And then we're going to subtract off, so minus that whole function g of x, and then put that whole thing over h. Okay, so we have the limit as h approaches 0. So g of x plus h, I see a 6. I see an x there, so I'm just going to put parentheses, but big enough to plug in x plus h and put a square. Minus 5, I see an x there, so put parentheses, so we can go back in and plug in x plus h. Minus 1. And now we're subtracting off that whole g of x function. So minus, let's put parentheses around this whole function g of x. So 6x squared minus 5x minus 1. And then we're putting that whole thing over h. And back in the beginning, I'm just going to go back and replace in x plus h wherever I left that parentheses. Okay, so we need to use some algebra to simplify this. Order of operations, you have to deal with exponents before multiplication. And so I cannot distribute the 6 inside that parentheses because of this square here. So to deal with that, we can rewrite that out as 6 all times x plus h times x plus h, that square. We can clean this up at the same time. So let's distribute this other piece. Let's distribute that -5 to the x plus h. So if we distribute that -5, we have minus 5x minus 5h. Bringing down this -1, so -1. And distributing this negative outside. So distributing -1 to positive 6x squared gives us minus 6x squared. Negative times this -5x is plus 5x. And negative times -1 is plus 1. All over h. So I need to bring down my 6. And if I FOILed x plus h times x plus h out, so x times x, that's x squared, x times h, that's a positive xh. This h times x, again, is, I can write it as x plus h, or xh. And then h times h, so plus h squared. In my bracket. But notice things cancel over here. I have a minus 5x and a positive 5x cancels. I have a -1 and a positive 1 cancels. So the only thing that's left up there besides that 6 times that quantity is that minus 5h and this minus 6x squared. And this is still all over h. This, just to save sometimes, this xh plus xh, this is plus 2xh. And let's distribute that 6. Okay. The limit is h to 0. 6 times x squared, so 6x squared. 6 times 2xh, so that's a positive 12xh. 6 times h squared, so plus 6h squared. Minus, bring down that 5h, and bring down the minus 6x squared. All over h. So again, things cancel. You have a 6x squared and a minus 6x squared. And notice that all the terms in that denominator that are left have an h in there. So we could pull out one of those h's in the numerator. So if you pull out an h from the 2xh, I'm sorry, not 2xh, 12xh, that's a 12x. Plus, if you pull out an h from the 6h squared, that's a 6h. And if you pull out an h from the 5h, minus 5h, you're left with minus 5. All over h. And I definitely need to bring down that limit because I haven't taken it yet. So notice you have an h in the numerator, h in the denominator, that now cancels. So now when we take the limit, as h goes to 0, of this 12x plus 6h minus 5. Well, plugging in 0, wherever you see an x, you have 12x minus 5. So we just found the derivative of f of x. So f prime of x is 12x squared, or no, not, it's just 12x minus 5. And I apologize, that's not f, it was g. Remember we called it g at the beginning? So this is actually g prime of x. So it tells us now we can find the derivative anywhere of g of x, that function g of x. So if we wanted to find g prime of -1, all we would have to do is go in here, wherever we saw an x in g prime of x, we would plug in -1. So this would equal (12) all times x, so we're going to plug in -1 there, minus 5. So this is -12 minus 5, which is -17. So that's telling me my slope when x is -1 on that parabola is negative, so it should be decreasing there. And it's decreasing at a rate of -17/1. Let me just kind of want to just go in and then just show you that on Desmos, the function, and then that derivative. Before we go in and look at that derivative though, let's find that equation of the tangent line at that value. So we can also graph that. So C. Let's find the equation. Oops. Of a tangent line. Of g of x when x equals -1. So remember, there's two things that you needed when you wanted to find the equation of a line. You need a point and we need the slope. Well, we actually just found the slope. So at x equals -1, you have -1. So was -17. So this is basically our slope of the line. And then we need to find a point of the line. Well, the point on the line is going to be the point of g of 1. So to find the point, on the tangent line. Well, we know that one point is going through the point on the graph. And so you're going to find, in our case, when x is -1, you're going to look at g of -1. Okay, so recall, let's recall what g of x was. So g of x in ours was 6x squared minus 5x. Oops, nope, that was wrong, right? Yeah, minus 5x minus 1. Let me just make sure I copied it down right originally. Yeah. So if we want to find g of -1, we're going back to our original function and plugging in -1 wherever we see an x. So we have 6, I see an x, that's going to be squared, minus 5, I see an x, minus 1. Plugging in -1 wherever you see an x, and then order of operations to simplify. So exponents first. -1 squared is 1 times the 6 in front is 6. -5 times -1, so plus 5 minus 1. 6 plus 5 is 11, minus 1 is 10. So we have a point at -1 and 10. And again, we said our slope was -17. So you can either use your point slope formula, you can use your slope intercept formula, however you want to do it. I tend to like using y equals mx plus b, but I think that your book shows you a little differently, so that might confuse you. But basically, I have my slope here, which is -17. I have a point on the line when x was -1. My y value here was 10. So if I can go back in, plug in those values, I can figure out what b is, and then I know what my slope of the line is. And it's also in the, I know what the equation of my tangent line is. And it's also in the form y equals mx plus b. So to me, that's easier to graph. So if I go back in and substitute in what I know into that equation, I have 10 has to equal my slope, which is -17, times x, which in this case is -1, plus b. So I have 10 is equal to -17 times -1 is +17 plus b. Solve for b, get 17 on the other side, we get b is equal to -7. So the equation of the tangent line of g of x at x equals -1 is y equals our slope, which is -17, times x plus b, which we just found to be -7. So -7. So -17x minus 7. So let me pull up. Oops, sorry. You'll see in a sec. Desmos. Okay, so we had our function y. It was equal to 6 squared. So I'm just plugging in that function, maybe. Minus 5x minus 1. Oops, I shouldn't have had the equal sign. We wanted to see what was happening when x was -1. So notice that with this graph, this is decreasing. We can see the graph is decreasing here at x equals -1. And what we just did then was we found that equation of the line that went through this point. That was the tangent line. We saw that that was -17x minus 7. So notice that this point, the blue line, actually, is going through that point, y equals 1. Oops, I was going to shift. And is a straight line. And this gives us that slope at this point. So if we found the equation of the line down here of the tangent line, it looks like my slope is going to be 0. This is probably my vertex down here. And my equation of the tangent line, if my slope is 0, is going to be a horizontal line. Where if I found the equation of the tangent line at x equals 1, notice that my slope would be positive. And so knowing what the slopes are of our derivative, we can tell actually where our graph would be decreasing and where it would be increasing. And we'll use that fact a little later in the next section. Okay, so this is probably a good spot to just take a break. Okay, so we're going to look at another example. In this example, we're going to find the equation of a secant line. through a point or points where x has been given values, and then we're going to find the equation of the tangent line when x has the first value. And so we're given the following, that f of x is equal to 6 minus x squared. And we want to first find the equation of the tangent line. Sorry, not tangent line, secant line. Secant line through the point where x has the given values. So find the equation of the secant line. And x is, in our case, -1, and x equals 3. Okay, so first I kind of want us to look at the graph of that. F of x is 6 minus x squared. So I notice that that is a parabola. My coefficient in front of the x squared is -1. So I notice that this is also, I can rewrite this if I want, as -x squared plus 6. So I know this plus 6 shifts my parabola, which is facing downwards, vertex at the origin, up 6 units. What do I know? And then an x equals -1. If I plug this value in where I see an x here, this would be 6 minus a -1 squared. So at -1, I get 5. +1, I would also get 5. Okay, so my parabola looks something like this. If I look at, so let me just plug these in. So just because I did it, f of -1, whenever we saw an x, we get 6 minus a -1. And then we're squaring that, -1. Order of operations, so 6 minus -1 quantity squared is 1, which was 5. So this gave us that point right here at -1, 5. So now looking at when x is 3, so looking at f of +3. So going in wherever we see an x and f of x, we got 6 minus, I see an x there, so I'm going to put a parentheses and square it. Put 3 inside the parentheses. So order of operations, this gives me 6 minus, well 3 squared is 9, and 6 minus 9 is -3. So at 3, I have -3. Let's say 3 is here. No. I'm going to say 3's here, just so it matches with my graph. Ish. So we have 3, -3, right here. So when it asked us for the equation of the secant line, it wants us to find this line that joins these 2 points. Okay, so we need 2 things. We need 1 point, which we have 2 of them, either -1,5 or 3, -3. And we need a slope of the line between those 2 points. And so to find the slope, we can look at our change in our y value. So if I start with this point on the left, my y value is 5 minus the y value on the left, -3, I'm on the right, all over -1 minus the x value over here, 3. So I get 5 minus -3, 5 plus 3 is 8, all over -1 minus 3, which is -4. So I find my slope is -2. Again, it doesn't matter which point we choose. So choose either one that we know that is on that secant line. And so if we use -1, 5. So it's up to you. You can use y minus y sub 1 is equal to your slope all times x minus x sub 1, which is your point slope formula. Or you can use how we were doing it before, which was the y equals mx plus b, which I tend to like to use. But if you're looking at how to do things in the book, they might be showing you it this way. Well, I have a point when y is 5. I know this is equal to my slope, which we found to be -2, all times x. Well, when y was 5, x was -1 plus b. So if I solve for b here, I have 5 is equal to, well, -2 times -1 is +2 plus b. Isolate b, I would subtract 2 on both sides of my equation. Well, 5 minus 2 is 3. So I get b is +3. So b is +3. My slope is -2. I have my equation of my line. So y is equal to my slope, -2, times x plus b, which was 3. So this is the equation of the secant line between x equals -1 and 3. But if I'm looking at the slope of the line at x equals -1, that is a good representation of what's going on there, right? If I look at what's happening at my slope of my tangent line, or I think about where that my headlights would be directing if I was on this right point, it would be directing upwards. I would have a positive slope. And so those two x values are not close enough to give us a really accurate interpretation of what's going on at any one of those values there. So the next part of that question was saying, let's find the equation of the tangent line at the first x value. And so we want to find the equation of the tangent line. So this line right here, when x is -1. Well, we already have part of the problem done for us. We know what that point is on this tangent line. Let's find the equation of the tangent line at x equals 1. So find equation of the tangent line. And x equals -1. Okay, so we again have a point, but we need the slope. And so the slope, we want to find that instantaneous rate of change, or what is happening when x is -1 there. And so we have to look at the limit. So there's a couple ways we can do this. We can go in and look at f of x plus ah minus f of x all over h as h goes to 0. This would give us the derivative of f of x. But we really want to find f prime of -1. So look at, if we go in here, let's just do this. Actually, I'm just going to do it the normal way. Let's just go in and plug in x plus h wherever we see an x in f of x. And recall our function f of x. I'm just going to write it up here again. That was equal to 6 minus x squared. So if I'm looking at f of x plus h, I'm going in here, wherever I see an x, I'm going to put a parentheses and replace it with x plus h. So I have 6 minus, I see an x there, put a square there on the parentheses and put inside the parentheses x plus h. And then minus, this is our f of x value. So minus this whole quantity, 6 minus x squared. And this is all put over h. So clean it up. So we got the limit as h goes to 0 of 6 minus, I need to FOIL out x plus h times x plus h. If you do that, you get x squared plus 2xh plus h squared. And then we need to distribute our negative inside this parentheses over here. So this would give me minus 6 plus x squared all over h. So again, we got to distribute this negative outside that parentheses. So bringing down the limit as h approaches 0 of 6. So this is going to give me minus x squared minus 2xh minus h squared minus 6 plus x squared all over h. So again, if you look in the numerator, a lot of things simplify and cancel out. This 6 and a minus 6 cancels. This negative x squared plus x squared cancels. And so all we're left with in the numerator is the negative 2xh minus h squared. And that's all over h. So we can pull that h out of the numerator and cancel with the h in the denominator. So if you had done that, you'd be left with just a negative 2x. And if I pull out an h from the h squared, I'm just left with minus h. So if h goes to 0, then you're left with just negative 2x. So that's the slope. We could find the slope anywhere at any x value on the line or on the equation y equals x squared. Sorry, 6 minus x squared. Now we wanted to find it at -1. So if we plug in -1 where we see an x in here, we get -2 times -1, which is at 2. So our slope of the tangent line at x equals -1 is 2. So we got our slope, which is 2, and we had our point when x was -1. I believe our y value was 5. Yeah, it was. So if we plug this into y equals mx plus b, we have our equation of the tangent line. Well, we find b, which would give us the equation of the tangent line. So our y value is 5 is equal to our slope we found to be 2 times x, which is -1 plus b. So 5 is equal to -2 plus b. So if I add 2 to both sides to get b by itself, b is equal to 7. So y is equal to our slope, 2, times x plus our b value, which is 7. If we looked at it, we could graph that line. It's going to be really small. So this line right here, this was at 6, this y value would be at 7, which looks good. And our slope is positive. For every 2 it rises, it's going to run over 1. Okay. So let me just talk about a couple of other things before I let you go. So notice if you had an equation of a line that was just a constant. So let's say y was equal to 3. If you graph this, wherever x value you have, your y value is always 3. So graphically what this looks like is a horizontal line. So it really doesn't matter what point you choose on this horizontal line. If you were trying to find the slope of this at any point, right? The slope is always going to be 0. So notice the slope is always 0 on the line. So if you're looking at the derivative of a constant, so if you have some function, f of x equals some constant k, and you take the derivative of that, f prime of x is going to equal 0. And so that's kind of the reasoning behind that. If we graph some constant k, instead of that being 3, this is some value of k. Any point on that line you choose, that slope would be 0. And we could show that if we looked at the difference quotient, look at the limit as h approaches 0. So if I'm looking at the limit as h approaches 0, well, f of x plus h I'm plugging in x plus h wherever I see an x in this function. I don't see an x in that function. So that's equal to k. Minus f of x, so minus k, all over h. So this gives me the limit as h goes to 0 of 0 over h. But 0 over some number other than 0 is always 0. And remember, h is going to 0. It's not actually going to be 0. So we just showed that the limit of a constant, or the derivative of a constant, is 0. So any questions on that? Okay, so this is probably a good spot to stop. And then we'll finish up on this section on Wednesday and then continue looking, using the derivative to help us graph functions to figure out where functions are positive, or slopes are positive, increasing, slopes are negative, where the graph is decreasing, or max and mins. Let me stop the video.